All right, everybody, we're going to do another little quick chemistry hit here to review intermolecular forces. Intermolecular forces are like the glue that holds one molecule to another. It is not the same as the glue that holds one atom to another in a bond. So this is what keeps water sticking to water when you take a big drink. Intermolecular forces affect things like boiling point, melting point, vapor pressure, heat of fusion, which if you remember is the energy it takes to melt something, and heat of vaporization, the energy it takes to boil something. So there are three big intermolecular forces that you are going to potentially see. You may see London dispersion forces. London dispersion forces occur in anything that has a Lewis structure that you can draw for it, but they play the biggest role in things that are non-polar compounds. But pretty much anything you draw a Lewis structure for has London dispersion forces in it. Dipole to dipole intermolecular forces only occur in things where they have polar bonds in them, or the molecule itself is polar, I should say, not polar bonds. Watch out there. So if it has a polar molecule, it can have a dipole to dipole interaction. And hydrogen bonding is like souped up extra strong dipole to dipole interaction that happens when you have a hydrogen connected to an F, connected to an O, or connected to an N. Remember that hydrogen bonding is not a true bond. It is just a molecular attraction. All of these, when we draw intermolecular forces, should be drawn kind of with a dotted line connected to them. So for instance, if I am talking about water, our old faithful companion here, you know, hopefully from practice, that oxygen is a partial negative, H is a partial positive, and water is probably the most polar substance that we deal with. So if I want to draw an intermolecular attraction between them, I'm going to take the H from one water and attract it with some dotted lines to the O on the opposite one. Remember, opposites attract. In the case of water, water would automatically have London dispersion forces because it is something that you could draw. It has covalent bonds in it. Because it's a polar molecule, it is also going to have dipole to dipole. And here, right here, this O to H and this O to H make it possible to hydrogen bond, but it is not the hydrogen bond, okay? Now, intermolecular forces cause all sorts of properties and differences that we can see. I'm going to go through two kinds of examples. One to show you the difference between having certain intermolecular forces and not having them, and then another one where we're talking about one specific type. So if we take a look at HCl versus NH3. I'm going to ask you, if you're going to look through this, take a second, pause the video, draw your Lewis structures, and then we'll go over these. Okay? So here is my Lewis structure for HCl. My Lewis structure for NH3 looks like this. So when I'm trying to figure out intermolecular forces, since I can draw a Lewis structure because these are covalent bonded, all of these are going to have London dispersion forces. Okay? Oop, that is not correct. LDF there. Okay? So first thing now I'll have is London dispersion forces. The next thing we're going to do is we're going to take a look and see if these are polar bonds. So if you recall, elements kind of in this upper right-hand corner here tend to have really high electronegativities. Hydrogen always has like a 2.1. So in the case of HCl, HCl is actually a polar bond, partially negative on the Cl, partially positive on the H. The same thing happens with the NH bond. It is partially negative around the nitrogen and partially positive around the hydrogen. You really should know by memory that the H's are partially positive and the N is partially negative. So get those electronegativities maybe written down, wouldn't be a terrible idea. So when we take a look at these, since this is a polar molecule here, because it's got a positive N and a negative N, this HCl has the ability to dipole interact. NH3, because it has the unshared pair of electrons, it makes it a polar molecule. So this guy here also has dipole to dipole. But here's where we see the separation. HCl is not capable of hydrogen bonding. The N to H bond here makes it so that NH3 can hydrogen bond. what you will see is you will see differences in the properties. I looked it up, and HCl has a boiling point of -85 degrees Celsius. NH3 has a boiling point of -33 degrees Celsius, which means that HCl has a harder time staying liquid than the NH3 does. And that's because NH3 has the ability to hydrogen bond, and so it has a stronger intermolecular force, keeping it in its liquid phase a little bit longer. Okay? The other thing I want to talk to you about with these is something like CH4 versus C6H4. Now, you aren't going to have to draw the Lewis structure for these, not H4, I'm sorry, H14. Don't draw the Lewis structures for these because it's not going to lead you to anything other than realizing that we have carbon with a lot of hydrogens, and in this case we have more carbon with more hydrogens. But it's only C to H, and you should know that C to H is a non-polar bond. That's something you should just know off the top of your head. So in this case, since they're both non-polar bonds and everything for both of those molecules, and they have similar formulas, they only have carbons and hydrogens, the only intermolecular force that they're going to have are going to be London dispersion forces. So in the case of this, we have to take a look at the size of the molecule to figure out which is going to have kind of the more dramatic London dispersion forces. In the case of C6H14, based on our data, the boiling point of C6H14 is 68 degrees. In the case of CH4, our boiling point is going to be -161 degrees Celsius. So you can see the boiling point here is very, very low, and that's because this is an incredibly small molecule. It has very little intermolecular forces between one CH4 and another CH4. But C6H14 is kind of a big mama, and so in this case, it's got more London dispersion forces because it has more electrons. And there is a term that they like to see. It is more polarizable. And what that means is that, if you remember, London dispersion forces are caused by something called an induced dipole, where electrons randomly flip into positions that give them positive and negative charges. If there are more electrons in a compound because it is more complex, you are going to have a situation where your more electrons can get more out of whack than they would with a smaller molecule. So in the case of C6H14, there are more electrons that can kind of get out of position and become more polar than something like CH4. And so we'd say, or explain the difference between the boiling point of C6H4 and CH4 by saying that the boiling point of C6H14 is higher because it has stronger London dispersion forces, because it has more electrons and is more polarizable than CH4, which has fewer electrons. All right? Hopefully that clears some stuff up. If you have any more questions, come and hang out and meet.